so this second part will be quite more technical. I just want to give you a glimpse of a couple of recent studies where we're trying to connect different aspects of cognition and neuroscience and algorithms for vision. So let's see. So I mentioned this diagram already. We can debate about exactly what current computational models capture, if anything at all, of this complex structure. But even those who believe that these our current deep convolutional network models constitute an approximation to some aspects of visual cortex, they're mostly talking about a few of the boxes in this in this complex diagram. So there's a lot more going on, and one of the things is that there are many more boxes, there are many more visual areas that people have not even studied in connection to computational models. And there are also many connections that are largely absent from this type of computational model. So in particular, horizontal connections, there are neurons that connect to each other within a layer. Top-down connections, there's a lot of information that comes from the top to the bottom that's largely unaccounted for in the vast majority, not in all of them, but in the vast majority of these computational models. And the possibility to really have dynamics and spatial-temporal integration. So I'd like to give you a flavor for some of these problems and how we are studying them in the context of visual recognition. So I will start with the role of horizontal connections in pattern completion. This work was done by three amazing students, Bill Lotter, Martin Schrim, Han-Ling Tang. So you probably, many of you, some of you may know some of these people. Incidentally, I put these QR codes. I'll put the slides in Dropbox. If people want to know more, you can go to our website and download data and code. And I'm a big fan of open science. I think that's very important. It's a separate conversation, but very happy to give you access to any further information you want. So the problem of visual pattern completion is ubiquitous in our daily life. We want to be able to recognize objects that are heavily occluded, or that where recognition is made more difficult in other ways. So this is one example of an unfortunate day in Piazza San Marco in Venezia in Italy. I'm pretty sure that you can all recognize many of these objects here. These things here, you probably can see only a few pixels, and you still know that they are ducks. This white thing here in the middle, it's mostly occluded. Again, you just have access to a couple of pixels, and yet you can tell that it's a table. You can recognize the chairs. You can recognize and understand a lot of what's going on, even though in some cases they may be up to 90% occluded. So we want to understand, A, whether current models can capture the ability to recognize objects from this, let's say, minimal information, or from these very heavily occluded images, and if not, what's missing. So the experiments that we run are very, very simple. So we took objects and we used a technique called bubbles to render objects through small apertures. So this is what the objects look like. So I'll refer to whole objects, those that have 100% visibility. And bubbles means that you're essentially looking at the world like this, so through small apertures. If you have a lot of apertures, there's a lot of visibility, the problem becomes easy. If you have very few bubbles, you have less information, the problem becomes much harder. So here we did a 5-way categorization task. Subjects have to recognize these objects, which are presented for a very brief amount of time, anywhere from 25 milliseconds to 150 milliseconds. So here I'm showing you behavioral performance on the y-axis as a function of the amount of visibility. So note that there's a cut here on the x-axis. So if you look at 100% visibility, people are at 100% essentially. This is a very, very easy task, okay? But as you go to the left and you have less and less visibility, the task becomes harder. And if we ignore for a second the colors, which represent the amount of exposure time to each image, we see that, as you would expect, there's a decrease in performance. But even up to 10, 20% visibility, people are still doing way above chance. Maybe, depending on which curve we're focusing on, 60, 70, 80% performance, even though the majority of the objects are occluded. So there's a strong robustness in our perception to limited visibility. Yes.
So what was the stimulus?
Yeah, so if I remember correctly, in this case, there were 25 different exemplars, 5 in each category. One of the tools that we have in psychophysics to try to study the dynamics of recognition is to use a technique called backward masking. So backward masking involves presenting the stimuli for a very brief amount of time, and then very, very quickly introducing a noise mask that looks more or less like the one I'm showing here. If the mask follows the stimulus immediately with a very, very short amount of time, then the initial stimulus becomes invisible, essentially. And if the mask, if you have a very long exposure, then the mask doesn't do anything. But there's some sweet spot in the middle where the mask can interrupt processing. And many people believe that backward masking essentially and largely interrupts top-down signals. So there's a feed-forward pass of information, there's a bottom-up pass of information, and the introduction of this backward mask mostly interacts and stops further processing of information. I'm not sure that this is entirely true, and we can debate about whether backward masking really isolates pure bottom-up processing. I think that that's not quite entirely right, but I think it's a decent approximation. Yes.
Which type of evidence?
Yeah, so one of them is actually neurophysiology. So people have shown that that some of the very fast responses are intact, but the later part of the neural response is abolished by the introduction of backward masking. So that's one argument to say that the first part of the neural response is largely feed forward, and that's not affected by masking. We can debate about. Again, I'm not entirely convinced, and but this is something that people have used as a very coarse behavioral proxy to separate bottom up and top down. And happy to discuss further. But
just current policy forward.
Right. Yeah, that's a very good point. So one way I would think about it is, I think discussing bottom up and top down is overly simplistic. So, for example, if we get into the details of the circuitry, you know this better than I do. Every cortical area has 6 different layers within. So for example, the feedback that happens between layer 2.5, layer 2.3, and layer 5.6, that's extremely fast. I'm very skeptical that that's interrupted by backward process. However, there are connections that go from IT to V1, for example. Those are pretty long connections. And those seem to take much longer. And therefore, it's more palatable to me, more possible that those may be interrupted by this kind of backward mask, but not the very, very short kind of feedback signals. Again, we can debate that. I still think that there will be interesting experiments to be done where people can really use modern techniques like optogenetics to really silence feedback and then show what happens with experiments like backward masking. Nobody has done that yet. I hope somebody will.
There are studies of like backward masking, but like simpler to like orientation, simple things, because these short-term connections are still like are not being interrupted. You should still be able to decode simpler things that like object identity. These long connections
There are plenty of studies with backward masking showing again that maybe let me first state this result and then we can come back to this. But you're right. So there are many studies of backward masking with simpler stimuli as well. Yes.
So when you talk about like top-down connections, you literally mean from the higher areas to lower, but not anything that's like lateral spread of activity or.
So the lateral spread of activity also seems to be pretty slow. The horizontal connections, there's some evidence suggesting that long-range horizontal connections within an area may also be pretty slow. So they may also be interrupted. Again, all of this is mostly conjecture. I don't think there is solid evidence showing. There's evidence showing that, for example, in V1, there's beautiful work from Thomas and many others. But before that, Charlie Gilbert and many others have measured signals that are presumably due to long-range horizontal interaction. So if they are farther away, they seem to be pretty slow. They may take up to 50 milliseconds or more. So you may get a response in V1, let's say at 50 milliseconds. Some of these long-range horizontal influences may happen at 100 milliseconds in V1. So they seem to be very slow. They might be interrupted here as well.
I mean, just wondering about the benefits of the asking versus just limiting presentation and reaction time.
Well, just limiting presentation time is not enough, right? So here we present the stimulus for 25 milliseconds, okay? But people have infinite time to respond. Right. So limiting. So another possibility would be to limit response time, and people have done those experiments. I'm a bit concerned that in those cases you're mostly interfering with the motor response, not with vision. So I'm not sure that limiting response time really gets at the question of what's bottom up and what's top down. There's a time that you need to actually say what you've seen, or press a key, or whatever, or press a lever, whatever format, and that I think is, I call that not vision, right? So another version is to just study neurons, right? And that gives us another proxy to when things happen, essentially. Okay, so anyway, so let me just state quickly that we got into a lot of these interesting discussions about backward masking, but let me just state the experiments, the observations, and then we can debate about what interpretation is. So this is the same format as before. We are seeing performance as a function of visibility. If we introduce the backward mask 150 milliseconds after the stimulus, so if you have 150 milliseconds to present the stimulus, that's the top line here, essentially nothing happens. That is, the backward masking has absolutely no effect. If we present the backward mask 25 milliseconds after the stimulus presentation, performance becomes almost chance, barely above chance. So the backward mask severely disrupts the effect of pattern completion, the ability to recognize heavily occluded objects under these conditions of very, very short exposure. So this is the interpretation here, that it costs about 50 milliseconds to be able to perform pattern completion. You need to have that amount of time. Okay, and we can debate whether this is bottom up or top down, but you need this additional 50 milliseconds of processing to be able to put the pieces together and be able to do pattern completion and recognize these heavily occluded objects. As a side note, when I use the word pattern completion, I mean purely visual recognition here. That is, we have an object that's heavily occluded and we want to know what it is. I am not claiming that we are imagining or reconstructing the whole object. So this sometimes goes in the computer vision literature by in-painting or by some sort of generative algorithm that actually draws what's happening in between. I'm not making any claims about that. All I'm claiming is that people can tell this is an animal, this is a chair, this is a vehicle, this is a face, etc. Okay, that's what I mean by pattern completion. Yes. Yeah, so that's a good question. And again, I apologize. I'm getting old, and with the mask sometimes it's hard to hear. So I lean towards people in thinking that will make me hear better. But anyway, so no, we didn't ask people to subjectively report what they perceive in these cases. Personally, just my own subjective experience. I don't see the whole lion. I can tell that that's a lion, but I don't do in painting. I don't do any kind of generative reconstruction of the whole object. Can I do it? Yes. You can ask me. Can you imagine the lion's mouth? Yes, I could. I could try to imagine that. That's not what I'm doing when I'm doing this kind of task. So I'm not claiming people don't have visual imagery. I'm not claiming people may be able to do all of these things. I'm just saying in this kind of experiment where we have a heavily occluded object and we ask you to do a forced choice, five-way categorization. I'm not claiming that that's what's happening. I don't think that's exactly what's happening. But we didn't really ask people to get a subjective report in this experiment. Okay, so I want to very quickly give you a glimpse of what happens inside the brain at the neurophysiological level. I showed you this lecture before. This is a recording in the human inferior temporal gyrus. This is a full, the responses to a full image. Again, just to orient yourself, these are 39 repetitions of the same image. On the y-axis is the intracranial field potential. On the x-axis is time. We see a very vigorous, clear response, even detectable in every single trial, without any processing, any massaging. You just plug the average response, and we see that there's a response to this signal. Now I'm going to show you individual trials of these heavily occluded images. So here are 4 individual trials of these heavily occluded images, and we can see that there is a lot of heterogeneity, there's a lot of variability from one trial to another, but in every single one of those cases, we can still see that there's a very vigorous and very clear response to the image, despite the fact that in this case there's about 85% occlusion. So even though there's minimal visibility, we can still recover a visually selective physiological signal from inferior temporal cortex. The numbers that you see there correspond to the time at which the trough, that is the minimum voltage, happened in these cases. And you can see that for the whole image, the fully visible image, that happens at about 150 milliseconds. And for all of these trials, you see in one case it's 190, in another case 290, 210, etc. So at the physiological level, there also seems to be a pretty significant delay in the responses to these heavily occluded images. Okay, so it costs about 50 milliseconds to perform pattern completion also at the physiological level. So at the behavioral level, you need more time to do pattern completion. At the physiological level, it also seems to be the case that we need additional time. Okay, so now let me tell you a little bit about computational models. So I'm showing here the same, in the same format, the performance as a function of visibility. The black curve is the unmasked human performance that I showed you earlier when I argued that that there's very strong robustness to heavy occlusion. And then each of the colors here correspond to another deep convolutional neural network. I'm not going to go into the details for the aficionados. Many of you may recognize some of these names. AlexNet is the one that I flashed very quickly earlier. There's BGC16, there's ResNet, Inception. We tried many different networks. They can all do this task, and they all fall quite short with respect to human performance. So none of these networks can perform at human levels in this task. So we did something very, very simple. So we based on the notion that backward masking might be interrupting some of these recurrent computations, based on the neuroanatomical idea that these connections, we know they exist, based on the idea that physiologically it also takes more time to process these types of images, we introduced horizontal recurrent connections at the top level only of one of these networks. This is just a toy model. We can build much better models now, but this is just a toy model just to illustrate as a proof of principle what happens when we have these recurrent connections. So here's what happens. So I'm going to talk first about the so-called RNNH model. So for the aficionados, this is what's called a Hopfield network. So here what we're doing is we're taking the FC7 layer of AlexNet. This is the topmost layer of AlexNet before the classification layer. And then we are adding all-to-all connectivity, that is horizontal connectivity within FC7. Importantly, we're not training the model with any of the occluded images. So we're not doing any backprop here. The way the weights are set in here is by following the Hebbian learning format that Hopfield proposed in his original work. Where basically we take the response to the fully visible images and we create attractors for each one of the fully visible images, okay? So these are called attractor networks specifically because the model can do pattern completion. That is, the model can do error correction, and you can start with incomplete patterns and basically land on the correct attractors. So even this very simple manipulation that has zero free parameters, there are no fine tuning. We're not taking very complex networks with lots of parameters and training the heck out of them. There are no free parameters here, and even this already improved performance as shown here by the RNNH curve. And then if you further train the network, that is, you do backprop, and that's what we call RNN5 here, then we can get even better performance and even match, or depending on where you are, surpass human performance in this task. Yes.
Can this only be done in the
we tried also. It could be done in some of the earlier levels as well. Most of our recordings were in the higher areas of visual cortex, and we thought that was more comparable. That's why we started at the top. In reality, as you know very well, there are probably these horizontal connections everywhere in every single layer.
So whether this change to the architecture of the model could also be easily implemented, and not just on.
I think it can. I think it's a bit more complex. The fully connected layer, every unit is distinct. In the other case, we have to ask questions like, do you want to do this at the kernel level or the unit level? I think in principle one could do this also. There's no reason not to be able to do all-to-all connectivity in COM1, for example. We may debate about exactly how to implement that. For example, one could do that at the kernel level, or one could do it at the individual unit level. But
it is possible to get a diagonal matrix version of the layer, but it will just become too many parameters.
Right. So one question is, in this particular case, the FC7 layer has 4,096 units. So this is essentially 4,096 choose two different weights. So in RNNH, we're not training anything. In RNN5, we're optimizing, we're doing backprop on these 4,096 choose two weights. If you do this in COM1, as you pointed out, I don't know what the numbers are, but they're enormous. Yeah.
And you do the vector on image training or on these images?
This was done on these images with cross-validation. That's what RNN5 is. There are other versions, and this is actually, we had extensive discussions about this. You can, for example, do this on some images. So this is done on cross-validation at the image level. If you do cross-validation at the category level, we had another version that we called RNN4, where we leave one category out, and it doesn't work as well as RNN5. So I think a lot of what's happening here in RNN5 is what I call memorization of the. It's not quite memorization. We're really doing cross-validation. We have different images, and I'll come back to what is really generalizing in this type of networks. Yeah. Yes.
So I noticed for this one and this figure, 4% visible, between 5%. There seems to be weird. It's more like any
You're saying that there's a major gap between 10 and 20%? Is that what you're saying?
Right. Like if the lines are separate, that's the most. If you have the separated the colors,
So you're asking if there's anything special about 10 to 20%? Is that the question, or?
Right.
Yeah.
You know, perceptually not the same thing. I think some insights. So it was also kind of similar between the of the human and the.
Yeah, it's an interesting question. I've never thought about it. just subjectively, I don't think that there's anything special about. I think this is a continuum in terms of percentage visibility. I've never noticed anything special about 10 to 20%, but I may very well be wrong. It's an interesting observation. I've never seen that. Adding an attractor network, recurrent computations to the top layer can improve performance. Training those can reach human level performance. So I want to just end this part with a very speculative notion that there may be, just roughly speaking, two operational modes. One is that it's basically feed forward and fast. The other one that's recurrent and slower. And one question that a lot of people ask about recurrent connections is, why do we need them at all if we can do what's called unfolding. Unfolding means that you take a network like the one shown here on the left, and you unfold each one of the recurrent connections to make a larger feed-forward network. In other words, you can mathematically transform a network with these blue recurrent connections into a larger feed-forward network. So a lot of people in computer science say, well, why do I care about recurrent connections if I can always make a deeper feed-forward network? And that has led to the race. I lost track of where things are. Maybe some of you know better than I do. There are networks now with 200 layers, maybe 500. I don't know what the latest is. But people keep adding more and more and more layers, and they think that maybe this is a way of implicitly implementing recurrent connectivity. So I'd like to argue that there are a couple of advantages to this type of recurrent connectivity as opposed to adding more layers. Some of them are biological in nature. So first of all, you're saving neurons, you're saving space. There are major constraints probably in evolution in terms of the size of our brains. So it's useful to save neurons. So we also save weights, and again, the same argument holds, okay? So, but the other one that I want to put forward is a more computational argument that has to do with the flexibility of computations. If you do this unfolding and you create a larger network, essentially you're stuck, meaning that once you unfold this network into this longer and deeper feed-forward architecture, that means that for every image, it has to go through this entire architecture, okay? Whereas with recurrent computations, you could have the same exact architecture work in a fast mode or in a slower mode. If the problem is very easy, that is, you don't need to have all of these recurrent computations. You can come up with a decision and a response in a largely manner without using any of these horizontal connectivity. Whereas in a problem that's very, very hard, you may need a lot of these additional computations, and you can implement them on the fly in a flexible manner by simply rerouting information as needed without getting stuck on this architecture. So by the way, this idea, I think you should also talk to Ko, who's hiding there in the back. They have basically a model that I think is very, very similar to this. I think they call it CoreNet, that I think is very similar in spirit to what I'm talking about here. It's not specific about pattern completion. There are many other images that are hard to recognize and where this kind of recurrent connectivity can be extremely useful. So one way to circumvent that, just as a technical note for the aficionados, one way to circumvent and bypass what I'm trying to say is to add bypass connections. Meaning I could connect in this long, deep network, I could connect layer 1 directly to layer 6. And indeed, people have tried that. Essentially, that's at the heart of things like REST nets. Okay? But of course, if you start doing a lot of these bypass connections, at the end, what you end up with is a network that looks more or less like the current one that we have here. So I think because of energetic considerations, because of space considerations, and because of the flexibility of computations, there's a lot of reasons why we may want to implement these kind of computations with recurrent circuits rather than keep adding more and more depth to the neural networks. And again, this is speculation to be debated.
The major difference between the two variants is that one has the weight sharing, the other does not.
Correct. Yes, absolutely.
In theory, the option B could allow operations that so the option A is in subspace of option B, right?
Correct. So what you're saying is in B, if you forget about weight sharing, there are many other networks in here. You can do a lot of other computations because you can have completely different weights. Absolutely. So that's again in this case I'm schematically on purpose having only 3 layers. But of course you could have a network that has all the richness of training weights by creating 10 layers. You don't. I'm trying to argue we don't need 200 layers. You may have a lot of richness in computations in 10 layers but you're right. If you have 200 layers and you don't have weight sharing, you have a much larger repertoire of potential computations, and you're absolutely right that A is a subset of B if you don't have weight sharing. That's a good point. Yeah. Yes.
So I'm not entirely sure if A is a subset of B because the A in, say, layer 2 gets to receive the output of layer 1 after like 1 time step. Even when the recurrent computations are happening, layer 2 gets to see the output of layer 1. But here, in sort of like you have to process through all of those sort of layers for layer 2 to actually.
Right. So I think it depends on the exact dynamics of how this is implemented. Let me in the simplest instantiation, we have layer 1. We have this recurrent computation here, and then that's passed on to layer 2. That is unfolded into the version in V, and that's a subset of B. Now, what you're talking about is a much more complex dynamics where all the time you're sending information one way and doing that is right. In that sense, this is not exactly a subset of the. But in the typical implementation of many of these networks, we think of we have one of these recurrent loops, and then you send the signal from layer 1 onto layer 2, and in that formulation, and then we unfold. Then A is strictly a subset of B. Of course, again, the dynamics in these networks is extremely primitive and very simple. The real dynamics in Cortex are more like what you are discussing, where all of these things are happening at the same time. Yes.
It's slightly related, but when we talk about the models, the looking stream, and we have all the impute areas in the hierarchy, and they're not 100. They're less than 10. But then when we think about, that we have layers in the cortex, and in each area there's going to be synapses. So if now thinking of a model with recurrent, how many processing blocks do you think that a model of the stream should we attempt to have? Like one per area, or should we have one per layer inside the area? I don't know, this is purely speculative.
Then the number is obviously 42. There's no one. So I don't know how many people are familiar with the Hitchhiker's Guide to the Galaxy or anyway, I have no idea. I think it's a great question. I don't know. So there's a lot of interesting, as you know very, very well, there's a lot of interesting questions. The terminology of layers is a little bit different from the way we use layers in Cortex. And the short answer, I don't know. I'll be happy to talk further. I don't know what's the right. This goes back to what's the right abstraction, and do we need to think about all of the amazing canonical microcircuits in Cortex between different layers? My suspicion is that we do need to think about all of those things, and I'd love to think more about those. I think those will be important. This is part of an axiom of existence in biology. A lot of us believe that if it's there, it's probably for a reason. I don't know for sure that that's true, but I think that some of the complexity of cortical canonical motifs with different layers, my guess is that a lot of those will be very relevant. We have some inklings that that's true in some processes like surround inhibition and so on. But I think that these are very primitive architectures, and there's plenty more to do. But I don't have a good answer.
This is a quick add-on. There is a paper by Shang Li and Tommy that has some theoretical discussion between the mapping isomorphism of a resin and an RNN.
Thank you. Yeah. So if you can post it in I don't know if Slack is working, but in the Dropbox otherwise. Yeah, that would be great. Yes. Okay. Oh, wow. Let me see. I really want to go to the third part, which is more speculative. So maybe what to do? Let me skip this work. Mengmi is around if you are interested in zero-shot visual search and eye movements. She has a beautiful model predicting how people move their eyes during visual search. So you'll see me now flashing lots of slides. I'll skip this part. Eye movements are central to visual cognition in primates, and we spend a lot of time trying to come up with models that implement top-down signals that can predict reasonably well eye movements. And we still have a lot to understand about eye movements. So if people are interested in this, please talk to me. I'm going to skip a lot of these. I want to tell you one more example and then jump on to the third part. So sorry for skipping lots of slides. Okay, all right. So I'll tell you the third, now second example of work that we've done recently, trying to go beyond some of the basic models of visual recognition to study a question that's very dear to my heart that has to do with contextual reasoning. So for that purpose, let me start with a very simple example. If you have seen me give a talk about this or seen this example before, then please shut up. Otherwise, raise your hand if you think you know what this object is. It's pretty hard, so don't be embarrassed if you don't. Fewer than 5% of people can recognize this object. There are no tricks, by the way. There's no occlusion here. This is a pretty common object, just that it's very, very hard to recognize. Okay, so I don't see any raised hands, or either you're all very shy. You know what it is? Okay. A hat? Okay. And any other guess? Did you say boat? Okay. Piano. Okay. Trolley bag. Okay. Sorry, I couldn't hear. Bathtub. Is that okay? All right. Okay, so now I'll give you the same image with full contextual information, and now maybe you've seen this. Then if we had more time, I would make you vote for all of these different options. So here it is. So now most people can recognize it quite well. So kudos to you for. I think you were pretty close. Anyway, I think this is not because. But because I'm presenting the image for a very long time. We've done lots of experiments where we present the images for a very brief amount of time. We can also control, and for eye movements, we can make sure that you don't move your eyes. And yet, once you have this full information, it becomes pretty easy to recognize. So I will contend that most of the models that we have today cannot do this type of very fast, very simple contextual reasoning that comes so natural and to us. So the fact that we have all of this additional information makes it very easy to recognize these objects. Okay, so we want to try to take initial steps to understand what's happening during contextual reasoning and how we use contextual information. So I will refer to images like these. So this is a couple wedding, perhaps. So this is a cake here. So I refer to this as the minimal context, and there are different images where we change the amount of contextual information that we present. And so we do experiments that look more or less like this. We ask people to fixate, we control where they're looking, we tell them where the object is going to be, and then we flash stimuli for a brief amount of time, in this case 200 milliseconds, in other cases even short amounts of time, and then we ask people to type in one word, and one word only, to describe what the object is. So if I'm not sure the timing will work here, but I'll try to run that experiment by you once. Okay, so here it goes. Okay, so first people fixate, and then we tell them this is where the object is going to be. So I'm going to flash very quickly an object in this location. Okay, so I want you to pay attention and just fixate there. This is going to be super fast. Don't blink, don't close your eyes, don't check your email, don't do anything else. All right, here goes. Okay, there it is. I think this is close to impossible for me. I think for most people, if anybody is courageous enough to try to say what that was.
Broccoli.
Broccoli, okay.
Muffin.
What?
A muffin.
Nothing.
Yeah.
Oh, okay, good. All right. Anyone else? No? Okay. All right. So now I'm going to do the same thing, but flashing the whole image. Okay. So again, remember this is the location. Okay, and that's the one. So now that's the whole image. Okay. All right. So again, we run this experiment. We're pretty sure you don't have lots of seconds to do reasoning. You're not solving fancy differential equations. You're not moving your eyes. You're looking at the same chunk of the image, and yet in one case you can recognize it quite well, in the other case you don't. Guy?
Previous slide said there is common sense. Why is this common sense?
All right, very good. Okay, so that's a remnant from another slide, I guess. But I really want to talk more with other people about what is common sense. I think this is our very primitive and extremely naive first attempt at what I think is one aspect that we can begin to study mechanistically about common sense. So I think common sense is a very complex word that incorporates lots and lots of different aspects of cognition. One of them is the notion that we know that spaghetti tend to be are maybe close to meatballs, or we know that people in airports have usually have luggage. Okay, so there's a lot of knowledge that we have about the world. There's a lot of correlations between objects. A computer may be correlated with keyboard and less correlated with the presence of an elephant. We also know about spatial arrangements of different objects. So I lump all of these things about that we know about the world in the word world knowledge. Josh has a different spin perhaps on this. He talks about core knowledge, about, I generally call it stuff we know about the world. I think we need some of this general stuff that we know about the world to be able to do contextual reasoning. So that in that sense, I refer to this as my own very timid first exploration of common sense. But we can debate about that nomenclature. All right, so here are your meatballs again. So we did many of these experiments. I'll just flash a couple of them very, very quickly. So here we're showing accuracy in behavioral experiments where people are doing visual recognition. With the so-called minimal context condition, this is the one that I showed you first, that was pretty hard, or the full context condition. If the objects are very, very large, so on the x-axis is the size of the object in degrees of visual angle. Roughly speaking, if you put your arm, if you extend your arm, the size of your thumb is about 1 or maybe 2 degrees of visual angle, okay? So those are the basic units that we use in vision to describe object sizes. Okay, so when the objects are very large, context does not play such a large effect. When the objects are are very small, there's a pretty substantial effect of context. Okay. This experiment, by the way, as a side note, is a bit different from the way we run most experiments. Most of the experiments that I run in my life are about force choice and way categorization. And more recently, I've become a bit concerned about doing forced and way categorization as a way of studying visual cognition. I think this idea of typing one word has a lot of pros, also some caveats, and I'll be happy to discuss some of the methodological issues around this way of testing vision compared to forced choice categorization experiments. Okay, but that's aside. Okay, so we built a model. I'm going to go very quickly now because I want to get to the third part. We built a model that incorporates some very, very basic ingredients of neuroscience to try to do the contextual reasoning. So the model basically has two streams. So we know that in visual cortex, there's a major eccentricity dependence in the size of the receptive fields. This is the reason why you cannot read outside of the fovea. So next time you're reading something, try to fixate, not move your eyes, and try to read a word that's a few sentences below or somewhere else on the page. It's basically impossible. So we think that we have perfect resolution everywhere, but we don't. As a matter of fact, if you're fixating on a given location, so I'm looking at Coco right now, okay? So basically, in my far periphery, I'm legally blind, okay? We see very, very little in the far periphery. The receptive fields are enormous. So one of the ways we see things in the periphery is when they move, okay? So if I'm fixating on Coco again, if I move my hand, I know it's there. If I don't, we're basically blind. We see very little in the far periphery. So this model implements some very simple version of that by having essentially one stream that processes only background, only contextual information, the other one that's processing the object. There are two deep convolutional neural networks. There's an attention module embedded, and I apologize, I'm going really fast here. All of this work was done by Mengmi Zhang, so feel free to talk to me or to her if you want to know more of the inner secrets of the architecture of the model. The model has dynamics that's implemented by something called an LSTM. This is a long short-term memory. Some of you are very familiar with this. This is one version of a recurrent model that can integrate information over time. And this is also where the two streams, the periphery and the object, are getting combined. So based on this, the model outputs a particular label, and then this process is iterated multiple times and until the object comes up with a guess, until the model comes up with a guess of what the object is. So the key ingredients here are the separation of a periphery and contextual information, the dynamic recurrent integration of the two over multiple time steps. So I showed you on the left the human behavioral data. Here I'm showing you the performance of this model on the same images in trying to do object recognition. We're not using the human behavioral data to train the model, so this is not one of those exercises where we're really trying to fit just data. And here, at least at the qualitative level, the model seems to capture some of these basic effects of contextual reasoning as a function of object size, how there's a facilitation of object recognition by contextual information. Okay, we did many more experiments. I'm just going to mention them very quickly. It's not just having more pixels that helps. For example, if we blur the contextual information, blurred context seems to be quite sufficient to improve recognition. So we don't need a super detailed recognition of each object in the periphery. And this is consistent with what I was telling you before, that we're basically blind in the far periphery. Low-level texture, however, is insufficient. So if we take all the peripheral information and we create what's called a Portilla-Simoncelli mask, meaning that we keep a lot of the low-level statistics of the stimulus, that's not sufficient for recognition. Humans as well as the model fail in that case. The contextual configuration is important. If you start scrambling the image, for example, the contextual facilitation disappears. And then several people have done this type of experiments where you paste an elephant inside the refrigerator or do incongruent context. And incongruent context impair visual recognition.
Have you done an experiment with Kreiman and Simoncelli with the localized receptive fields? I would assume that maybe that would give in and we could potentially figure it out. That's a conjecture.
So the texture here was generated by this Portilla-Simoncelli algorithm. What you may be referring to is the V2 model that Simoncelli did. We have not done that. That's an interesting question. We have not done that. So, yeah.
You tried using like any of those off-the-shelf, just like image segmentation models to see how they do?
Off-the-shelf image segmentation. I think we have not. We compare with a lot of other models. So you can go into the paper here. I'm going to skip the comparison. We compare with many other models, but I don't think that we compare with instant segmentation models. I may be wrong, but I don't think we did. Yes.
Might be interesting to try it with object images, because my guess is that the word context may not count there.
With what? With
ObjectNet images.
ObjectNet. Oh yeah, no, absolutely. Yeah. So Andre and Boris did a Herculean work. I think this may have been mentioned already in the tutorials, where they collected all of this data set called ObjectNet, which I would encourage everyone to take a look at, where they basically have objects that are in strange angles or in different configurations, and you're absolutely right. Would be very. And the background is changed as well. This is an amazing data set. It stress tests a lot of computational models. It shows also a major gap in computer vision systems. And I agree with you that it would be very interesting to test this. We have not. Yeah.
So for treatments with contacts that involves knowledge about the world, right? Like the writing in the cake. So that involves some semantic information. But for the model, what is the context?
That's a very good question. I think a true comparison of machines and humans is always very challenging, exactly for those reasons. So the models are trained in this case with MS COCO, which has a lot of statistical correlations between objects. So the models may learn that chairs are associated with tables. So there is the models do learn a lot of these, but how to compare that with humans in a fair way, I think is very, very challenging. So again, with this very simple kind of stimuli, I would argue that we have a first order approximation to that in here. Now, if you start looking at the details, there is no quantitative map. That is, for example, the model here is still below human level performance. If you look at the number here for the first bar, the black bar, right? So the model does not quite capture all the semantics that humans are. This is only a very primitive first step, if you will. But there is some sense in which the model can know some aspects of the world through training by in these data sets. Okay, but I agree with you. There's much more to a story than this. This is just an initial step in this direction. Yes.
The model trained the paradigm or trained the more standard approach of valuing like this. So yes, you can require additional knowledge of the way that runs the whole process.
I'm sorry, I'm not sure I got every single word that you said, but I think the question was whether the model was trained in exactly the same way. Largely, the model was trained with MS COCO images, also in this kind of task. There's a couple of differences. One of them is that for humans, we're asking them to type one word, and they can type anything they want. The model only has an n-way categorization task. That's important, and that because of that, they're not really directly comparable in quantitative terms either. And again, I'm sorry if I didn't get all the words that you said. There's a lot of knowledge about the world that humans have, and I'm not claiming that our model is anywhere close to understanding all the complex semantics of contextual information. This is only a very primitive step, which I think is a step in the right direction, but there's certainly much more. I'm not sure if this answers your entire question. Okay, all right. I'm sorry again. I find it hard to. The acoustics here is not very good. So please do come and talk to me more about this. Okay. All right. So again, the models. These models still fail in major ways, and this is related to the ObjectNet data set. If you do things like put a backpack in a plate of meatloaf and mashed potatoes, none of the models can detect this backpack. You have this giant chair in a parking lot. Models again fail miserably. We're now using a couple of computer graphics tools to be able to generate and really control images in all kinds of ways. So we entitled the paper "Pigs Can Fly." We can make objects that are flying, and therefore we can violate many aspects of what I refer to as, in a fancy way, as common sense. We can violate many aspects of common sense, right? So we can violate the statistics of object co-occurrences. We can make objects that are not supported, therefore violate gravity. It doesn't really violate gravity. It's just an unlikely scenario to have a cup that's flying in the air. We can violate the relative object sizes. We can make a chair that's 5 times as big as a car, et cetera, et cetera. So these computer graphics tools are allowing us to do a lot of interesting things and ask questions in a very controlled fashion. And again, if you're interested in this, come and talk to me or to Magni. Okay, so I wanna stop this part here and switch to the last part of what I wanted to say now, which is meant to be entertaining, provocative, and jumping from one random topic to another, mostly to stimulate discussions. Yes, as I switch slides, ask me. Yes.
Yeah, I mean, it's still related to the previous one, but like, human spatial temporal reasoning from common sense, like where was the temporal divide?
Good question. So okay, you already saw all the slides. Anyway, so sorry. Yeah, so two things. One is the model does have some very primitive dynamics. The model is iterating over time. There's an LSTM module that's integrating over. But in the human experiments, I didn't show you that. We did a couple of experiments with backward masking and with different exposure times, also to try to assess when contextual information matters. And I skipped all of that, and if you're interested, I would be happy to share the data and show you what the results are. So the short answer is that people can do a lot of this contextual reasoning quite fast, much faster than I would have expected. But at some point, it breaks down and it may require what might be top-down signals and this type of temporal integration. But everything I showed you, at least up to now, is a single saccade, a single fixation, no saccades, very integration within a couple of 100 milliseconds. But that's a good question, and I have lots more to say about that. I'm happy to talk more about it. All right. Okay, so the last part, this is meant to be mostly jumping from one topic to another, mostly trying to be provocative and talk about several different loose ends, Hilbert questions, and random questions in the spirit of what Tommy said at the end last time as well. Okay, so here are a couple of major challenges ahead in vision. So one of them is, as you know very well, there are these adversarial attacks where you can take an image, you can add noise, and make models think that the object is something else, right? So you can take this panda, add minimal amounts of noise, and convert that into a given, okay? And this is quite peculiar. If you want to have models that really match our human perception, we want models to have the kind of robustness that our perception has. Our visual systems can also be deceived. I deceived you earlier with the Al Gore and Bill Clinton image. There are lots of visual illusions to deceive our perception as well. But if we have a real model of vision, we want to be able to deceive it in the same way that we deceive humans. So talk to Casper here is very interested in adversarial images. Tiago also has done beautiful work with adversarial images and can tell you much more about this. Networks struggle with continual learning. This is the problem of you learn a couple of object classes. Let's say you learn how to discriminate cups from scissors. Now you want to learn. Now you learn something new. Let's say chairs versus tables. And by and large, networks forget what they've learned initially. Humans are not like that. So when you go from math class to English, you don't forget everything you learned in math, mostly. Okay, so I think this ability to do continual learning and learn things without forgetting previous things, you can learn how to play Go without forgetting how to play chess, etc. This continues to be a major problem for computer vision. And then in general, the lack of knowledge integration, common sense, contextual reasoning. So I want to talk a little bit about this image. Some of you may have seen me or other people talk about this image before. Let's say that we have a system that can perfectly recognize and do instant segmentation of every object. We're not quite there yet, but let's say that we do. So we have systems that can recognize every person, maybe segment them. Let's say that we can even recognize mirrors. By the way, mirrors I think may be hard to recognize. It's hard to to know what's a reflection or not. But let's say that we do recognize the floor, the lockers, absolutely everything in here. I think it's very clear that that even in that case, we're still very far from understanding what's really going on in this image. So I flashed this image. This image is intended to be somewhat humorous. This gentleman here, whose birthday I think is either today or yesterday, and is celebrating across the street in Martha's Vineyard, he's being playful here, okay? So to understand what's going on here, you need to know that humans are often a bit self-conscious about their weight. You need to understand that contraption there is a scale, that the gentleman here is trying to measure his weight. You need to know that Obama is exerting a force on this scale here, that will alter the measurement. Furthermore, you need to understand that all of these other people are in on the joke, they understand what's going on, whereas he's not. He cannot see Obama on the reflection, he's focused on the measurement, etc. So there's a huge amount of things that you understand. You don't need to be an erudite and solve complex differential equations. Maybe you've never seen this particular image before. Maybe you've never seen someone play a joke on somebody else by stepping on the scale behind them. Even if you've never experienced this, and this is the very first time that you see this, you can understand a huge amount of information about this image. I think that we are extremely far from having computational models that can be anywhere close to this kind of understanding on an image. Even perfect instance segmentation algorithms that can label everything, and we're not quite there yet. It's easy to fool current algorithms in a lot of ways, like making pandas look like gibbons, okay? But even if we have robust algorithms, even if we have perfect object labels, algorithms that can produce perfect object labels, we're extremely far from real image understanding. And I don't know exactly what the path is to get here. And I'll be very, very excited to talk more with people if people have ideas. How do we go from labeling objects to understanding on an image? So one example of that, and we were talking about this in Captain Kidd the other day with some of you, is how to understand humor. And I think it's basically impossible to have algorithms that can really predict humor. Not impossible in the physics sense of a law. I think eventually we will have algorithms. I personally believe that anything that humans can do, we will have algorithms that can do it too. As a matter of fact, I think the algorithms will do it better for anything that humans do. But right now, with current algorithms, with current technologies, with current ideas, I think we're extremely far. So here's the kind of challenge that I talked to some people about. We can take images. I want to avoid text just to keep the problem circumscribed and easy. We can rate how funny they are. And some of us ran an experiment with drunk people in Captain Kidd the other day. We can predict how funny the images are, okay, or even say funny or not, okay, and then throw your best tools. Take your best algorithms, and short of very simple spurious correlations. So, for example, if you have all the funny pictures be black and white and all the non-funny ones be color, yes, of course, you can very easily create algorithms that will do that, okay? But if you don't do that kind of trick, and there are lots of correlations and biases that you need to be concerned about. But if we control for all of those things, I think that we don't have anything that would be anywhere close to being able to understand why this particular image is intended to be humorous or not, or the same thing with the Obama picture that I mentioned before. Okay, I'm jumping here from one topic to another. I just want to throw a lot of random thoughts at you to, again, mostly for brainstorming. And again, feel free to shout if you disagree. Coco told me that he believes that we can solve the humor question now. I disagree with that. We can continue the discussion. Okay, so here's a remark on a task that's very common in computer vision these days. It's called VQA, visual question answering. The idea is you have an image, you have a question, you have to answer that question. There are lots of algorithms that have claimed that they can do this sort of thing. So here's an example. I apologize if the font is too small. I don't know if you can read it from there, but hopefully you're very young and you can. So here there's an image. The question here is, what color is the floor? Okay, and here is a human answering brown. That's the correct answer. And the colors that you see overlaid on that image, this red circle and so on, these are attention maps. They are calculated with a fancy method where you have an image that's blurred, you click on different locations to deblur it, and you see what people pay more attention to. Another way to do this is to measure eye movements, to see what people pay attention to in the image. Okay, so here to answer this question, people pay attention to this location. Okay, so there are many models. In this case, we used a state-of-the-art transformer model that was trained to solve this kind of problem, and the model got it right. So it's also said brown. We also can ask what the model pays attention to, and in this case, there was a pretty good correlation of 0.55 between what the model pays attention to and humans. By the way, in computer vision and in biology in general, if you get a correlation of 0.55, you get quite excited. That's a real thing. Okay. But then we did things like shuffle the order of words. Okay. So we asked the model, is color floor what then? Okay. I don't know what that means. So we just randomly shuffled the words, and the model answered brown. Okay. So the model basically didn't care about the order of the words. So we did a lot of other manipulations, like removing some of the words, And then as a control, we also had a completely different question, right? So we showed this picture and said, is this singles or doubles? And the model answered singles. So the model, of course, this is the wrong answer. The answer was what we're expecting is for this image was brown, but of course, if you don't know the question, you cannot do it, right? So here you have a correlation of 0.02 that doesn't make any sense. Of course, that this is just a control. Okay? But if you shuffle the words, you get a correlation of 0.56 here, and you get the right answer. So many of what we think are the most exciting VQA answering algorithms, you shuffle the words, or you remove some of the words, and nothing happens. You get basically the same answer, you get the same attention. I don't think these models really understand much of what's going on in the image.
Or what would be the answer if you shuffle the words to humans? Because if I see E squared for what I would maybe infer the question and so on.
You may be right. We didn't do that experiment here, and you may be right here. In this case, you may be right. We haven't done it. I think it's an interesting question. You may even pay attention to the same areas. You may be right. It's a good point. Yeah, absolutely. Yeah.
There are these like garden path sentences, right? Which are not for you can make like the old and the boat. So the old man gives you a very different interpretation of the sentence, but when you complete the sentence building the boat, it's like the old people are driving the boat. It completely changes. These models will still show the same behavior, but like humans will differ. So there are sentences.
Yeah, you're absolutely right. And in fact, here we did this in a very simple way, but you can also ask the question in a different way such that the answer should be different. And we didn't do that here, but you're right. And that's a way to try to do a double dissociation with humans. Here's just another example. I will skip some of the other examples and we can, again, we can discuss further. Just to point that I'm a bit skeptical about what these VQA answering systems actually are doing. How do models get such high performance? So I want to make a couple of philosophical remarks about generalization, about cross-validation, look up tables very quickly. This is what we do by cross-validation. We take data, we separate it into a training set and a test set. And of course we do that because we want to avoid overfitting. Okay, so what does cross-validation really mean in the context of many of these tasks? So here let me start by what I call trivial generalization. I think we will all agree that this is not very interesting. Imagine that I take training data, let's say ImageNet, and I train my favorite algorithm to do object recognition there, and then I do the following manipulation. I change one pixel in every image, okay, and I get test data. It's legitimate test data. It's a different train. All the images in the test data are different from those in the training set. Okay, they have one pixel deliberately. One pixel is different. Okay, and of course my algorithm will probably work extremely well. Okay, so this is what I call trivial generalization. I don't think this is very interesting. I'm not claiming this is what algorithms are doing. Okay, I just want to point to one extreme of cross-validation, which is legitimate cross-validation, but pretty boring, not interesting cross-validation. Okay. Here's the other extreme. Imagine that we have an algorithm that's trained on clip art, okay? And here I didn't do it right, but imagine that we have exactly the same categories on the left and on the right, okay? So we train an algorithm on clip art for these categories, and then we test it with real photographs, okay? I don't think that there's any algorithm right now that would work, and they would fail miserably. In fact, we have data showing that these algorithms fail quite miserably in this case. Okay, and then of course, most of you will complain and say, oh, that's an unfair comparison, right? Of course, there is no magic generalization. You cannot go from clip art to photographs. That's too large a generalization, right? So in between the sort of trivial generalization and what I call here magic generalization, most of what we're doing in AI these days is somewhere in between, and usually not very well defined. So this is basically at the heart of what some people refer to as in distribution or out of distribution. Usually it's not very well defined what the distribution actually is. So I think this is important because in one case I'm super excited. If you show me an algorithm that can solve this problem, I find it's amazing. If you show me an algorithm that solves a problem with one pixel change, I say, well, whatever, you're just memorizing the data, right? So the difference between a lookup table and generalization is the details of how you implement actually cross-validation, what's in the training set, what's in the test set, how much you can actually generalize or not. And I think in many of our studies, that's not clear. That's ill-defined. I think it's important to get more serious about it and define that better. And I should point out that it's not clear how much animals can generalize. So we have this intuition, and many psychology will tell you, oh, humans can do 0-shot learning or -1-shot learning. I don't know. Humans can do all kinds of generalization. Most people have never measured these things in a rigorous way. So I don't know that humans can actually look at clip art and actually recognize photographs and without ever having been exposed to photographs at all. So I don't know that humans can do any real true generalization either. So we can debate about exactly, and again, it all boils down to the details of what's the distribution, what people have learned or not. With humans, it's much harder because usually we don't have real access to, it's cruel to deprive them of certain visual experiences, right? So we don't have easy ways to test them on these questions. But this question, I think, is at the heart of what we mean by building real intelligent algorithms. Okay. I'm jumping to other topics. A lot of people talk about deep convolutional neural networks as black boxes. I hate that nomenclature. I don't agree. I think they are not black boxes at all. I think that we understand deep convolutional networks extremely well. In fact, we're understanding so well that we're using the best way to describe them, which is the language of mathematics. I think we should always describe things with mathematics, not with words. So I think that this myth that neural networks are black boxes is erroneous. And yet there may be many situations where you do really want to have more and better interpretability, okay? And Casper here is a great advocate of this. Talk to him. Happy to talk more about what are the conditions under which we want mathematics and what are the conditions under which we actually do want to have interpretability. By the way, this is, even has legal implications. Some of you may know that in Europe, they have passed laws now regulating when you can or cannot use algorithms for different kinds of purposes, depending on whether you can translate and interpret their activity in a language-based manner. So I don't think that there are black boxes. I think that we can describe the inner secrets of what's happening very, very well. Yet I'm not against the notion that in some cases we may need to have better interpretability, but I don't like calling them black boxes. All right, very quickly, I'm jumping from one topic to another, mostly to stimulate further discussions and to throw a lot of ideas at you. I told you that I was dissatisfied with this Bill Clinton story and this way of just throwing pictures and hoping for the best. We spent a lot of time with my friends Carlos Ponce, Will Xiao, Marshall Livingston, trying to come up with a more automatic way of trying to use what we understand now about convolutional neural networks to be able to design stimuli or to figure out what neurons like. I think March will talk a little bit about this algorithm, so I won't. So this is a way in which we basically were generating images with a deep convolutional neural network turned upside down as a generator to try to, in a closed loop fashion, figure out what neurons respond best to. And the short answer is that we can drive neurons to very high firing rates. That is, we can discover what neurons like with this much more automatic approach without having to worry about whether neurons respond to famous people or not, or to Bill Clinton or not, or to faces or chairs. We can just start with noise and automatically try to discover neuronal preferences. At the same time, there was another approach that was carried out by Jim DiCarlo's lab, and Jim is going to talk about this more tomorrow. We tried to do some very basic comparisons of these two approaches, and it's quite interesting and intriguing that it's not very clear that these are convergent in any way. And I think that this is pointing out to the fact that the models of neural responses fail to generalize. So here's one of the exercises that I think was mentioned in the tutorials that we and many other people have done. This was pioneered by Dan Yamens and Jim DiCarlo, where you take some images and then you feed a model and you try to feed neuronal responses. So on the x-axis are the firing rates from neurons in inferior temporal cortex to a set of images, and on the y-axis so on the x-axis are the predicted firing rates, on the y-axis are the observed firing rates. So this is a model that can, using cross-validation, again with all the caveats I mentioned about cross-validation, information, you can actually feed neuronal responses quite well. You have enough parameters, of course, you can feed things, okay? So you do this, and then the question is, can you actually predict responses to completely novel images? So we tried that with our images, the ones that we generated with our algorithm, and the model is quite off. So this is the case where the model, within the set of natural images that we use, the model can feed those responses. When we test it without retraining, without doing more manipulation of parameters on a completely different set of images, we didn't do that well. That's the orange line. And then when we use a computational model similar to what Jim was doing to try to feed neural responses and create images, again, the model were quite off. So these models, I think, they fail to generalize in a major way. So within the training set, or things that look similar to a training set, we can feed neural responses. When we go very far away from that, things start to become very complicated. So I don't think that we still, I still do think we have a very long way to go to have good models that can predict neural responses. So very quickly, I'm going to finish quite soon. Just to flash another image, this is beautiful work that David Cox did with Bill Lauder, trying to build an unsupervised or self-supervised model for aspects of visual cognition. What's quite exciting here, what they try to do is, and again, I'm sorry I'm skipping a lot of the details here, they are trying to build a model that will predict the next frame in a video sequence. So this model is inspired by the idea of predictive coding in neuroscience. There's a seminal paper by Rao and Ballard in 1999. So this is a model that has not only bottom-up signals, but also top-down connections. These top-down connections are providing a predictive signal. And these models are trained to try to take a video sequence, in this case, a video sequence from a self-driving car, documenting what's happening in the streets and predicting what's going to happen next. So these GIF files that you're seeing here, on top you have the actual video, on the bottom part you have the prediction. So as you can see, they're not perfect, but they're quite good. They can predict the next frame quite well. And remarkably, and this seemed like magic to me, it was quite exciting to see that Bill tried this, the responses of these units in these models do seem to have a lot of properties that resemble aspects of both psychophysics and behavior, as well as some aspects of neuronal responses. And this is pretty vague. I'll be happy to discuss more. Here are the papers if people want to read more. This idea of unsupervised learning, I think, is also quite interesting and important because as I'm sure most of you have thought about this, we are usually not trained by using backpropagation and millions of examples, but rather by basically having exposure to the world, understanding the basic structure of the world, and other ways of training these models might be quite appealing to be able to come up with more biologically palatable, more biologically plausible ways of thinking about cortex. Okay, so the last thing I want to say, just again to tease people here and further discussions, there are books written by lots and lots of people about why humans are so beautiful and so special. This is the anthropomorphic notion of the supremacy of Homo sapiens. The people claim that humans are the only animals that, and you can finish that sentence in a lot of different ways. Here are just a few examples. Some people think that humans are the only ones that have language. Noam Chomsky wrote a whole book about this. The title of the book is quite explicit. It says, "Why Only Us?" Some people think that humans are the only ones that have consciousness. I think that some people said that when Tommy was mentioning this the other day, that they show true general intelligence, that they have free will, they can make true long-term plans, create art, tell jokes. I put a question mark here. I'm skeptical about every single one of these claims. I believe in the continuity of evolution. Homo sapiens are beautiful for sure. I don't have anything against Homo sapiens, but there's just one tiny branch here in this amazing diversity of species. I'm very skeptical that, yes, there are lots of things that humans do that are quite extraordinary, but I think that it's very important to study animal models to better understand human cognition as well. One of the things that I thought was really true is that humans are the only animals that wear Nike shoes. Unfortunately, I was proven wrong. I looked this up on Google, and lo and behold, Anyway, so I thought this was, I could make one true statement about humans and why they're special. Anyway, but I want to finish with this again, now instead of comparing with other animals, comparing humans with machines. And I think the answer to all of these, as of 2021, is yes. So I don't think that we have machines that have language, consciousness, true intelligence, free will, can make long-term plans, create art, or tell jokes. So I think that as of 2021, the answer to all of this is vehemently, undoubtedly, for sure, yes. However, I think that we will. I think that this is up to you. I have very high confidence in your talents. I think the next generation, there are lots of exciting problems to work on. And I do think that, I don't want to say when, because I'm for sure I'm going to be wrong, but I think that the answer to all of these questions will eventually be no. That is, we will have machines that can solve all of these and many other more exciting problems. And here's a robot wearing Nike shoes, so machines can wear Nike shoes. But otherwise, I think that we will be able to to have AI that can solve all of these problems. And I really hope that all of you will be involved in this exciting adventure. That's it. Thank you.